Hello, this is Murungwa Sydney, student number 2342648. Me and my group will be here to solve fluid dynamics problem using FlowNext simulation software and analyzation.
My name is Alec Mkarati, student number 2215206, with a 100% contribution to this project.
My name is Mubiane Vari.
This is a simple fluid dynamics problem that was taken from the Fluid Mechanics textbook, the 5th edition. This problem from the part 3, problem number 130, whereby there was use of a pump to draw water from the tank. There were 2 nozzles fitted on both sides of the pump. We added 2 extra luces to fit the constraints, and the following assumptions were made. We assumed uniform velocity profile since we have a fully developed flow where the flow is uniform. We assumed steady flow because all the properties remained constant throughout the problem. We assumed constant density as only the water was used throughout the question. We assumed that no shaft work due to the presence of pump and no moving parts, hence potential energy is negligible. Based on these assumptions, the implementation of continuity equation and Bernoulli's equation will be relevant.
In this slide, I'll be explaining the analytical approach of finding the solution. First of all, we have assumptions that we are written on the top right corner here. The first assumption is uniform velocity profile, where we have constant velocity, as this is a fully developed flow, therefore automatically we will have uniform flow. The second assumption is that we have steady flow, because this is a laminar flow and the properties remain constant throughout. Thirdly, we have the constant density, as we are only using water as our substance. There's only presence of water in this problem. And the final assumption is no shaft work. This is brought about because we have pump and there are no moving parts, and therefore the potential energy is negligible. Coming to the method of finding the answer, based on the assumptions above, we have implemented the continuity equation, as this is a one-dimensional flow, and also we included the Bernoulli's equation due to no friction present on the flow, therefore no losses. Then we do the maths so that we can find the value of 64.59 kilowatts as our final answer.
After finding the analytical solution of the problem, we used FlowNext simulation tool to develop a numerical solution to the pipe flow. Our system started at a reservoir containing water at density 998 kilograms per cubic meter at temperature 10 degrees Celsius. We used basic pipes with head loss of 5 meters, and at an elevation of 2 meters from the water surface, we added an elbow similarly to the one on the problem. The flow rate was constant at 220 meters cubed per hour throughout the system. Minor losses at the elbow were added to the system. The velocity at the nozzle was found to be 31.12 meters per second. The pump generated an overall power of 43.349 kilowatts from a pump head of 24.161 meters. The table here indicates the results obtained from analytical solution and numerical solution. From both methods, the velocity at the nozzle exit is the same. There is a difference between the head pump for analytical and the one from numerical solution, wherein the one for numerical solution is almost half the one from the analytical solution. Because of this, the power delivered to the water from analytical solution was higher than the one for numerical solution. The difference in power would be because of the pump selected for numerical solution in the simulation and the losses that were neglected in numerical analysis.